Welcome back, everyone. We're going to jump ahead to lesson 9 now. And in this lesson, we're going to talk about sampling again. We've talked about sampling a little bit and the importance of how we collect samples. And then we're also going to start talking about margin of error. We've talked about samples before. Basically, the bigger your sample size, the less likely the results are to be biased. The reason we collect samples is, as it says here, is often too difficult and frankly impossible to collect data from the entire population. So what statisticians will often do is they will take several smaller samples and then use the results of those samples to make a estimate or possible conclusion about the entire population. The key here is that one sample is certainly not enough to form an unbiased conclusion. And the reason being is there could be a lot of variability, which is why we'd like to collect more than one sample before we make a conclusion. Kind of going along with sampling is this idea of a margin of error. Some of you may have heard of this concept of a margin of error. Usually you'll see it talked about with political polls around election time, where different candidates are in the polls. Usually, if you look at the fine print, there's usually a margin of error involved. And the textbook definition is the maximum expected difference between the estimated value and the actual value. So the estimated value is what you conclude based on the data and the samples that you collect, and the actual value is what actually ends up happening. So the margin of error is usually plus or minus a certain number of percent. So the layman's term definition is that the actual value is somewhere within the interval. So you have an estimate, you have a margin of error that creates an interval, and usually your actual value will end up somewhere within that interval if you collected your samples well enough without bias and randomly. And the way we're going to find the margin of error in this unit is to essentially double the standard deviation. If you double the standard deviation, that will tell you your margin of error, and then you can simply add that or subtract that from your estimate to get your interval where the actual value will be. So that interval, based on the margin of error, will capture the actual value 95% of the time. That is how we interpret the margin of error. So if we want to capture the actual, if we want to increase this percentage, so if we want to capture the actual value, say 98% or 99% of the time, if we increase the percentage, we're going to increase the margin of error. Conversely, if I were to lower this percentage, so if I wanted an interval that captured the actual value, say 85% of the time instead of 95, so decreasing that percentage would decrease the margin of error. Lastly, sample size will affect margin of error. Okay. We've talked about that the larger the sample size, the better your results are going to be. The less likely your results are going to be biased. So if you increase your sample size, your margin of error is going to go down. Okay, the amount of variability will go down. And then opposite, if you decrease the sample size, you will increase the margin of error. They'll be more likely to have different sources of bias or error within your results. So with that in mind, let's go ahead and take a look at the examples for this unit or for this lesson. So a political campaign sends volunteers out into the various parts of the state to get a sense of how well their candidate will do in an upcoming election. 30 volunteers each get a random sample of 10 people in the state and find the proportion. The proportion is the percentage. They find the proportion of the people who are expecting to vote for their candidate. The sample proportions are summarized in the histogram here. The mean of these sample proportions is 0.55. Okay, so that would be about 55%. And the standard deviation is 0.15. So number one, recall that for normally distributed data, about 95% of the data is within 2 standard deviations of the mean. What percentage of the sample proportions are within 2 standard deviations of the mean for these data? Does this match what we expect from approximately normally distributed data? Explain or show your reasoning. So first thing we'll do is we know that my mean is 0.55 and my standard deviation is 0.15. So if we want to find how much is within 2 standard deviations, the first thing I need to do is I need to find the value that represents 2 standard deviations above the mean, and I need to find the value that's 2 standard deviations below the mean. So 2 standard deviations above the mean would mean I'd have to take the mean and add, because I'm doing 2 standard deviations above, I would have to add the standard deviation twice. If I wanted to find 3 standard deviations above the mean, I would have to take the mean and add the standard deviation 3 times. So 0.55 plus 0.15 plus 0.15 is going to be 0.85. So 0.85 is approximately here on the histogram. Okay. And 2 standard deviations below the mean, well, now we're going to take the mean, and instead of adding the standard deviation twice, we're going to subtract the standard deviation twice. All right, so that will give me 0.25. So 0.25 is in the middle right here. Okay, so anything between these 2 values is within 2 standard deviations of the mean. So to figure out that percentage, let's first figure out the total, what our total amount is. So this is 1, this is 4, 6, 8, and then we have 6 again, 4, and 1. So let's add all this together. So this will be 12 plus 8 is 20. 12 plus 8 is 20. 24, 28, 29, 30. So the total number, the total amount of data is 30. And then whatever's in the middle, in the middle of that interval, so that would be everything in here that I'm shading in yellow, is within 2 standard deviations of the mean. Now the problem is this particular one right here, we don't know where that falls. We don't know whether it falls below 0.25. If we count it, let's just for the sake of this count it. So that would mean all of this is within 2 standard deviations of the mean. The only one that isn't is this one right here. So that would mean 29 out of 30 is within 2 standard deviations of the mean. So 29 out of 30, okay, 29 out of 30, I'm just going to divide that on my phone, on the calculator on my phone, and I get approximately 0.967, which is 96.7%. So to answer this question, What percentage of sample proportions are within 2 standard deviations of the mean for these data? We got 96.7%. Now, let's say we decided not to count this one right here. If we didn't count this one here, it would be 28 out of 30. And if I did 28 out of 30, again, I'm just going to calculate this using the calculator on my phone. I get 0.933, which is 93.3%. Either way, we would expect that 95% should be within 2. And either way, we would get 93% or 96%. Is that pretty darn close to 95? Yes, it is. So to answer the second question verbally, does this match what we expect from approximately normally distributed data? Yes, it does. Is it perfect? No. But is it pretty darn close? Yes, it is. Okay, so that's number one. Number two, estimates for population characteristics are usually given along with a margin of error. Okay, and I've talked about what the margin of error is. Okay, margin of error is the maximum expected difference between the estimate of the population characteristic and the actual population characteristic. This was in our notes. Each of the sample proportions are good estimates of the population proportions, so we should give a margin of error that contains about 95% of the sample proportions to be reasonably sure that the actual population proportion is in the range between the mean minus the margin of error to the mean plus the margin of error. What margin of error should be given along with the estimate of 0.55 for this population proportion? So I'm actually going to do number 2 on this here. So for number 2, okay, remember to find the margin of error. If we go back to our lesson notes, we basically have to double the standard deviation. Okay, so the margin of error, so I'm going to abbreviate MOE. Sometimes it'll be abbreviated ME. It means the same thing, but the margin of error is 2 times the standard deviation. So in this case, it's going to be 2 times 0.15, which is 0.3. So what margin of error should be given along with this? It would be 0.3. Okay, so what this means is that if I were to take the mean and add the margin of error, so 0.55 plus 0.3, that would be 0.85 or 85%. Okay, and if I were to take the mean and subtract the margin of error, so 0.55 minus 0.3, I would get 0.25 or 25%. So that would give me an interval of 25% to 85%. So what that margin of error tells me is that in this case, we were talking about the proportion or the percentage of people that would vote for a particular candidate. So what this means is that the actual percentage of people who vote for this candidate is going to be somewhere between 25 and 85%, somewhere between this interval. That is what I meant by the interval will capture the actual value 95% of the time. The actual value is somewhere within this interval. Okay, so by adding and subtracting the margin of error from the mean, that gives me the interval where we are reasonably sure that the actual value will be. So again, in this case, the actual percentage of people who vote for this candidate will be somewhere between 25% and 85%. And that is it for this lesson.